calculate the density of a cylinder, the density, Greek symbol rho, is simply its mass over its volume. Now, the volume of a cylinder, of course, simply volume is just the area of one end, which is pi times the radius squared, since it's round, times the height of the cylinder, h. However, what we've measured is diameter d, not radius r. So we need to realise, to make this a little bit simpler, that instead of having the radius in there, the diameter over 2, half the diameter is the radius, so instead of r squared I'll write that, we'll stick the pi around there and the h there, and then simplifying that, the density of the cylinder is simply 2 squared is 4 on the bottom line there, so it becomes a 4 on the top line, m over pi times d squared times h. Now, having seen that, we can now write an expression for how good our result is. The uncertainty in the density, first off, let's look at our measurement of mass. If I'm out by maybe 1 or 2 parts in 1,000 in my measurement of mass, that will affect my measurement of density by also 1 or 2 parts in 1,000. And so the fractional error in the density, delta rho over rho, will depend on the fractional error or uncertainty in the mass, the delta m over m. There's also an h on the bottom line too. If I'm out by 1 part in 1,000 in my height measurement, then I'll be out by another part in 1,000 in the density measurement. And so I'll add delta h over h there. Now, diameter comes into the equation twice. D squared is d times d. So if I'm out by maybe, let's say, 1 part in 100 in my diameter measurement, then because I'm having d appear twice as d times d, that'll make twice that effect, 2 parts in 100 as the error in the density. So I have to write 2 delta d over d. So let's put in now the values that we have measured. And I'll just move that up a little bit there. And what we've measured for the mass, we measured 70.97 plus or minus 0.01 of a gram. Now for the height measurement, I originally measured it in millimetres, but I'm going to now quote it in centimetres. Instead of 29.64 millimetres, I'm going to write that as 2.964 plus or minus 0.002 centimetres. And for my diameter measurement, again I measured 19.05 plus or minus 0.01 millimetres. I'm going to write my diameter also in centimetres and make it 1.905 plus or minus 0.001 centimetres. My reason for doing that is if I have mass in grams and my other dimensions in centimetres, my density will come out as grams per cubic centimetre. And if you do the arithmetic, we're using 70.97 for mass, 2.964 for height, 1.905 for diameter, we'll calculate that the density is 8.4007 grams per cubic centimetre. But how good is that measurement? What we're going to have to do is work out each of these parts, delta m over m, delta h over h, and 2 delta d over d, cross multiply up the row to work out that delta rho. So delta rho, cross multiplying up the row, will be 8.4007, and delta m over m, 0.01 over 70.97, plus delta h over h will be 0.002 over 2.964 plus 2 times delta d over d, 2 times 0.001 over 1.905. All of that calculated out gives us 0.0156. So now looking at my final results for density and the uncertainty, the leading digits are 1 in my case, and so I'm justified in quoting the last digit there. So I'm going to write the uncertainty as plus or minus 0.1016, rounding that to two significant figures, and then I'm going to round that to match. So I round it up to that space there, round it up to the third decimal place, rounding that up, it'll be 8.40, that rounding up will be 1. So 8.401 plus or minus 0.016 grams per centimetre cubed, which translates to, in SI units, 8401 plus or minus 16 kilograms per metre cubed.